How plants triggered mass extinctions. The history of life on Earth is often viewed through a lens of progressive harmony. A slow climb from the primeval slime toward the complex, balanced ecosystems we recognize today. In this narrative, plants are the benevolent providers, the foundational bedrock of the food web, the producers of oxygen, and the sequesterers of carbon. They are the passive backdrop against which the drama of animal evolution plays out. We tend to view mass extinctions as events inflicted upon life by external forces. The fiery descent of an asteroid, the eruption of a supervolcano, or the harsh shifts of solar output. However, the geological record reveals a darker, more complex truth. The most chaotic, destructive, and transformative events in planetary history were not always caused by rocks falling from the sky. Some were engineered by life itself. Specifically, the evolution of complex land plants was not merely a biological curiosity, but a geological cataclysm that dismantled the Earth's climate system, poisoned the oceans, and triggered one of the 5 greatest mass extinctions in history. This is the story of the Devonian Period and the rise of the green killers. To understand how a tree can kill a fish, one must first divest oneself of the idea that the biosphere and the geosphere are separate entities. They are intimately locked in a chemical dance. The composition of the atmosphere, the acidity of the oceans, and the temperature of the globe are dictated by the flow of elements like carbon, phosphorus, and oxygen. For billions of years, this flow was regulated by simple microbial life and tectonic activity. But when plants began their conquest of the continents, they introduced a new, aggressive variable into this equation. They did not just live on the land, they mined it. They broke it. And in doing so, they unleashed a cascade of chemical consequences that brought the Paleozoic world to its knees. The context of the Devonian Earth. The Devonian Period, spanning from approximately 419 to 359 million years ago, is traditionally known as the Age of Fishes. This title is well-earned. The oceans of the Devonian were teeming with a diversity of marine life that has rarely been matched since. It was a world of placoderms, armored fish with bone-crushing jaws like the formidable Dunkleosteus, which could grow to the size of a modern school bus. Ancient sharks patrolled the waters, and the seafloors were covered in vast, intricate reef systems, built not by modern corals, but by stromatoporoids and tabulate corals. These reefs were the metropolises of the ancient world, stable and biodiverse, having thrived for millions of years in a warm greenhouse climate. The land at the beginning of this period was a different story. It was not barren, but it was alien. The terrestrial flora consisted mostly of small, non-vascular plants, mosses and liverworts that hug the damp edges of water bodies. There were no forests. There were no deep soils. The interior of the continents was largely rock and sand, a vast reddish wasteland washed by rain but untouched by roots. The evolutionary leap. The trigger for the catastrophe began with a series of evolutionary innovations. Plants, driven by the pressure to compete for sunlight and spores, began to grow up and down. The development of vascular tissue, lignin and xylem, allowed plants to transport water against gravity, standing tall and rigid. This led to the evolution of the first true trees, such as Archaeopteris. Archaeopteris was a marvel of biological engineering. It possessed fern-like fronds but a trunk like a modern conifer, capable of growing upwards of 30 meters. For the first time in history, the Earth had a canopy. But the true revolution, the one that would doom the oceans, was happening underground. To support these massive vertical structures, plants needed anchors and a steady supply of nutrients. They evolved roots. The mechanism of destruction was not violence, but chemistry. Early roots were not just passive straws sucking up water. They were active geological agents. The roots of Archaeopteryx and its kin penetrated deep into the continental crust, cracking bedrock and infiltrating crevices. To extract nutrients like calcium, magnesium, and phosphorus from the stone, these plants engaged in aggressive chemical warfare. They secreted organic acids and chelating agents, and they fostered symbiotic relationships with mycorrhizal fungi that could dissolve mineral lattices. This process is known as biologically enhanced chemical weathering. Before the rise of deep-rooted plants, rock weathering was a slow, abiotic process driven by rain and wind. Plants accelerated this process by orders of magnitude. They turned the continental crust into soil, the phosphorus bomb. The creation of the first deep soils, or pedogenesis, seemed like a benign development. It allowed for more plant growth and the stabilization of land surfaces. However, the liberation of nutrients from the rock had a fatal side effect. Phosphorus is a limiting nutrient in most ecosystems. Life craves it, but it is usually locked away in minerals. The new, deep-rooted forests mined phosphorus on an industrial scale. Since the vascular land plants had not yet evolved efficient mechanisms to retain all this liberated nutrient, and because the newly formed soils were easily washed away by surface runoff, vast quantities of phosphate were flushed into the river systems. These rivers acted as arteries, pumping a constant stream of fertilizer into the epicontinental seas and the open ocean. What followed was a global eutrophication event of apocalyptic proportions. In the modern world, we see localized versions of this, when agricultural runoff causes algal blooms in lakes or coastal zones. In the late Devonian, this occurred on a planetary scale. The sudden influx of phosphorus and other nutrients fed an explosion of algae and cyanobacteria in the surface waters of the oceans. These microscopic organisms reproduced frantically, turning clear blue seas into a turbid green soup. The suffocation of the seas. The bloom itself was not the killer. The killing began when the algae died. As billions of tons of algal biomass sank into the depths, it was consumed by aerobic bacteria. These decomposers, in their feeding frenzy, stripped the water column of dissolved oxygen. The ocean began to suffocate. This phenomenon, known as anoxia, spread from the bottom up. The deep oceans became toxic dead zones, and as the oxygen-depleted waters transgressed onto the continental shelves, they smothered the great reefs. The armored fish, the trilobites, and the ammonoids had nowhere to run. They were trapped in a gasping world. The geological record of the late Devonian is marked by black shales, dark, organic-rich sedimentary rocks that form only in the absence of oxygen. These black shales are the tombstones of the Devonian oceans, preserving the chemical signature of a dying world. The carbon crisis and global cooling. The assault on the biosphere was two-pronged. While the oceans were choking, the atmosphere was freezing. The same chemical weathering process that released phosphorus also had a profound impact on the global carbon cycle. When silicate rocks are weathered by acid, formed from atmospheric CO2 dissolving in rainwater and root secretions, the chemical reaction consumes carbon dioxide from the atmosphere and converts it into bicarbonate, which is eventually washed into the ocean and precipitated as limestone. In essence, the weathering of rocks pumps CO2 out of the air and locks it into stone. Furthermore, the explosion of plant biomass on land represented a massive new sink for organic carbon. Plants pulled CO2 from the air to build their trunks and leaves. When these plants died, much of that carbon was buried in the newly forming soils or washed into anoxic basins where it could not decay. This rapid drawdown of atmospheric carbon dioxide, a potent greenhouse gas, broke the back of the Devonian greenhouse climate. Temperatures plummeted. The Earth, which had been a tropical hothouse, swung violently toward an icehouse state. Glaciers began to form over the southern supercontinent of Gondwana. The cooling intensified the extinction. Many of the marine species, particularly the reef builders, were adapted to warm, stable waters. They had no tolerance for the cold. As the ice caps grew, sea levels fell, exposing the continental shelves and destroying the shallow water habitats where most marine life resided. The combination of anoxia, lack of oxygen, and glaciation, cold and habitat loss, created a kill mechanism that few could escape. This double blow is the hallmark of the Kellwasser event, one of the distinct pulses of extinction within the late Devonian. The Kellwasser event. The late Devonian mass extinction was not a single day of doom, but a crisis spread over several million years, punctuated by severe pulses. The Kellwasser event, occurring around 372 million years ago, was the first and most devastating of these pulses. It sits at the boundary of the Frasnian and Femmenian stages. The fossil record shows a catastrophic collapse of the coral stromatoporoid reef systems. These reefs, which had been the largest distinct structures made by living organisms, were obliterated. They would not recover for tens of millions of years. When reefs finally returned in the Mesozoic, they were built by entirely different organisms, the ancestors of modern scleractinian corals. The Devonian reefs were effectively erased from history. During the Kellwasser event, we see a selective pattern of extinction that supports the plant trigger hypothesis. Bottom-dwelling organisms and those unable to tolerate low oxygen levels were hit the hardest. Deep-water species that were already adapted to lower oxygen survived better than the shallow water specialists. This aligns perfectly with the model of rising anoxic waters. Additionally, the geological strata from this time show spikes in geochemical markers like uranium and molybdenum isotopes, which are proxies for low oxygen conditions. The Hindenburg event. Millions of years after the Kellwasser event, the ecosystem was still reeling. The surviving fauna attempted to adapt to the new, colder, and more volatile world. But the plants were not done. The relentless weathering and the continued expansion of seed plants led to a second major pulse of extinction at the Devonian Carboniferous boundary, known as the Hindenburg event, roughly 359 million years ago. If the Kellwasser event was the suffocation, the Hindenburg event was the deep freeze. The Hindenburg event is associated with a massive drop in sea level and severe glaciation. It decimated the survivors of the Kellwasser crisis. This event was the final nail in the coffin for the placoderms. The armored giants like Dunkleosteus vanished forever, clearing the ecological stage for the rise of ray-finned fish and sharks. The Hindenburg event also affected the land. The early tetrapods, our ancestors that had just begun to drag themselves out of the water, suffered heavy losses. Evolution was bottlenecked. The diversity of vertebrates crashed, leading to a period known as Roemer's Gap, a 15-million-year hiatus in the fossil record where few tetrapod fossils are found. It was a time of biological silence following the botanical storm. The rise of fire. The impact of plants on the Earth system did not stop with the Devonian. In fact, the changes initiated in the Devonian set the stage for the bizarre world of the Carboniferous period that followed. The relentless photosynthesis of the expanding land forests continued to pump oxygen into the atmosphere. By the Carboniferous, atmospheric oxygen levels soared to perhaps 35%, compared to 21% today. This hyper-oxygenated atmosphere allowed for the evolution of giant arthropods, dragonflies with the wingspans of eagles and millipedes the length of cars. But it also made the world incredibly flammable. The Carboniferous was a world of charcoal. The vast swamp forests, the source of much of the world's coal deposits today, burned regularly. Evidence of massive wildfires is preserved in the fossil record. The plants had created an atmosphere that was hostile to the stability of their own ecosystems. This period ended with the Carboniferous rainforest collapse, another minor extinction event driven by climate shifts. As the climate dried out and the great lycopod rainforests fragmented into isolated islands of vegetation. Once again, the dynamics of plant life were driving the geological and climatic destiny of the planet. The Gaia versus Medea hypothesis. The story of the Devonian extinction challenges our philosophical view of life. In the 1970s, James Lovelock proposed the Gaia hypothesis, which suggests that life interacts with the inorganic surroundings on Earth to form a synergistic, self-regulating, complex system that helps to maintain and perpetuate the conditions for life on the planet. Gaia suggests that life makes the Earth more habitable. The Devonian plant explosion suggests the opposite. Paleontologist Peter Ward has proposed a counter-argument known as the Medea hypothesis, named after the Greek mythological figure who killed her own children. The Medea hypothesis argues that life is inherently self-destructive. When a species or a group of species gains a dominant ecological advantage, it often alters the environment in ways that are detrimental to the rest of the biosphere and ultimately to itself. The plants of the Devonian fit the Medea profile perfectly. They were too successful. They stripped the air of carbon so efficiently that they plunged the world into an ice age. They unleashed so much nutrient flow that they poisoned the very oceans that sustained the water cycle. They were not stewards of the earth. They were reckless engineers. The evolutionary innovation of the seed was another critical factor. The first forests were composed of spore-bearing plants that required moisture to reproduce. This limited them to lowlands and wet environments. With the evolution of the seed, plants broke their tether to the water. They could colonize the drier uplands. This meant that weathering was no longer confined to river valleys and coastlines. It spread to the interiors of continents. The volume of rock being chemically attacked increased, further driving the CO2 drawdown and nutrient release. The conquest of the land was total, and the consequences were total. The lag time of ecology. One might ask why the ecosystem did not balance itself out more quickly. Why didn't animals evolve to eat the plants and release the carbon back into the atmosphere? The answer lies in the chemical composition of the early trees. To stand tall, these plants evolved lignin, a complex organic polymer that provides structural support. Lignin is incredibly tough and chemically stable. In the Devonian and Carboniferous, there were very few organisms, bacteria or fungi, that had evolved the enzymatic machinery to digest lignin. When these trees died, they did not rot in the way a modern log rots. They accumulated. Massive layers of undecomposed wood piled up, eventually becoming coal. Because the carbon in this wood was not being recycled back into the atmosphere through decomposition, it was effectively removed from the system. This imbalance, high production of biomass, low decomposition, was a primary driver of the global cooling. It took tens of millions of years for the fungal kingdom to catch up and evolve the white rot fungi capable of breaking down lignin efficiently. Until then, the plants held the carbon cycle hostage, the modern parallels. Studying the Devonian extinction is not merely an exercise in paleobotanical curiosity. It offers chilling parallels to our modern crisis. Today, we are witnessing rapid changes in ocean chemistry, acidification and anoxia, and atmospheric composition. In the Devonian, the driver was the expansion of plants. Today, it is human industrial activity. However, the mechanisms are frighteningly similar. We see coastal eutrophication creating dead zones in the Gulf of Mexico and the Baltic Sea, caused by the runoff of artificial fertilizers. This is a localized, anthropogenic reenactment of the Devonian nutrient crisis. We are seeing the collapse of coral reefs due to thermal stress and acidification, mirroring the demise of the stromatoporoid reefs. The difference is the speed. The Devonian crisis unfolded over millions of years. We are engineering similar changes in centuries. Furthermore, the concept of geoengineering, the deliberate modification of the Earth's climate to combat global warming, often includes proposals to plant trillions of trees, or to seed the oceans with iron to stimulate algal blooms. The history of the Devonians serves as a warning label for such interventions. Biological agents are unpredictable. When we unleash a new biological force or drastically alter the biomass of the planet, the side effects can cascade through the geological cycles in ways we cannot fully anticipate. The plants of the Devonian did not intend to freeze the world or suffocate the fish, but their blind biological imperative to grow and reproduce had exactly that effect. The survivor's world. The world that emerged from the ruins of the Devonian was fundamentally different. The oceans were repopulated by new groups. The placoderms were gone, replaced by the cartilaginous and bony fish that dominate today. On land, the tetrapods that survived the bottleneck began to diversify, eventually leading to the reptiles, mammals, and birds. The plants, too, changed. The dominance of the spore-bearing giants waned, giving way to the gymnosperms, the seed plants that would dominate the Mesozoic. The soil itself was different. The deep, chemically weathered soils created by the Devonian forests permanently altered the geology of the Earth. They changed how rivers flowed. Before plants, rivers were mostly braided streams, wide and shallow, washing constantly over the landscape. The stabilizing effect of roots created meandering rivers with stable banks and deep channels. This change in fluvial architecture altered sedimentary deposition and created new habitats for freshwater life. The plants had terraformed the planet, making it more hospitable for themselves and their terrestrial descendants, even as they devastated the marine realm. The role of black shales. The economic legacy of this extinction is vast. The black shales, deposited during the anoxic events of the Devonian, are the source rocks for much of the world's oil and gas. The Marcellus Shale in the United States, for example, is a Devonian formation. When we burn natural gas today, we are releasing the solar energy trapped by Devonian algae that bloomed and died in a suffocated ocean 370 million years ago. The energy driving our modern civilization is the direct result of the mass extinction triggered by the first forests. We are burning the ghosts of the Kellwasser event. Detailed mechanisms of silicate weathering. To fully appreciate the science-true aspect, one must look closely at the silicate weathering feedback loop. The reaction can be simplified as follows. Carbon dioxide gas dissolves in rainwater to form weak carbonic acid. This acid falls on silicate rocks like granite or basalt. The acid attacks the crystal lattice of the minerals, releasing ions, calcium, magnesium, potassium, sodium, and silicic acid, and converting the CO2 into bicarbonate ions. These ions are carried by groundwater into rivers and eventually to the ocean. In the ocean, organisms like corals and plankton use the calcium and bicarbonate to build their shells out of calcium carbonate. When these organisms die, their shells settle to the seafloor and become limestone. The net effect is that for every molecule of calcium silicate weathered, one molecule of CO2 is removed from the atmosphere and locked in rock. Before plants, this process was limited by the surface area of rock exposed to rain. Plants, with their invasive roots, increased the surface area of rock available for weathering exponentially. They also pumped CO2 into the soil through their roots, root respiration, and the decomposition of organic matter. Soil CO2 concentrations can be 10 to 100 times higher than atmospheric concentrations. This highly acidic soil water attacks rock much more ferociously than rainwater alone. This biological amplification of weathering is estimated to have increased the rate of CO2 removal by a factor of 5 to 10 during the Devonian. This was the thermoregulator of the planet breaking down, the Algeo-Scheffler hypothesis. The theory that plants caused the late Devonian extinction is largely credited to geologists Thomas Algeo and Stephen Scheffler. In the late 1990s and early 2000s, they synthesized geochemical data, fossil evidence, and modeling to propose the root hypothesis. They argued that the timing of the spread of Archaeopteros forests coincides perfectly with the onset of marine anoxia and global cooling. Their work challenged the traditional view of mass extinctions. Previous theories for the Devonian crisis included asteroid impacts, the Alamo impact, and the Siljan Ring, but these impact craters do not line up well with the extinction pulses in time, nor are they large enough to explain a global biological crisis of this magnitude. Volcanism was also a suspect, specifically the Viliui traps in Siberia. While volcanism likely played a role, especially in the later stages, the isotopic signature of the carbon shift strongly points to a biological organic source rather than a volcanic one. The plant hypothesis remains the most robust explanation that accounts for the specific pattern of nutrient, carbon, and oxygen shifts observed in the rock record. The persistence of the green killer. It is ironic that the very traits that make plants essential for our survival today, oxygen production and carbon sequestration, were the agents of destruction in the deep past. It serves as a reminder that good and bad in ecology are relative terms. An organism simply does what it evolved to do. The consequences depend on the context of the planetary system at that moment. In the Devonian, the planetary system was not ready for trees. The buffer capacity of the oceans and the atmosphere was overwhelmed by the sudden efficiency of vascular plants. The Earth had to find a new equilibrium. This new equilibrium eventually included animals that could eat the plants and recycle the carbon, and fungi that could rot the wood. But getting there required a painful transition, a biological bottleneck where the old order had to die. The physiological evolution of the plants themselves is a marvel of adaptation. The development of stomata, microscopic pores on leaves, allowed plants to regulate gas exchange. They could open to let CO2 in and close to prevent water loss. This efficiency allowed them to colonize arid environments. But as atmospheric CO2 levels dropped due to their own activity, plants had to evolve even more stomata to capture the thinning carbon dioxide. This increased the water cycle on land, as more transpiration from leaves meant more clouds and more rain, which in turn fueled even more weathering. It was a positive feedback loop of cooling. The angiosperm revolution. While the Devonian is the prime example, plants have disrupted the biosphere at other times. The Cretaceous terrestrial revolution, roughly 100 million years ago, saw the rise of angiosperms, the flowering plants. Before this, the world was dominated by ferns, cycads, and conifers. Flowering plants grew faster, cycled nutrients more rapidly, and had different relationships with soil microbes. Some scientists argue that the rise of angiosperms accelerated weathering rates again, potentially contributing to the cooling trend of the late Cretaceous, though not to the catastrophic extent of the Devonian. They also fundamentally changed the diet of dinosaurs. The herbivorous dinosaurs had to adapt to a new food source that was richer in energy, but perhaps chemically defended in new ways. The interplay between plant evolution and animal evolution is a constant arms race. The Azolla event. Another striking example of botanical climate control occurred much later, in the Eocene epoch, about 49 million years ago. The Earth was in a hot greenhouse state. The Arctic Ocean was an enclosed basin, similar to the modern Black Sea, but fresh water at the surface. A tiny aquatic fern called Azolla began to grow in the Arctic Ocean. Azolla is a superplant. It grows with incredible speed and can fix nitrogen from the air. Under the long summer days of the Arctic, azolla bloomed in mats that covered the entire polar ocean. When these mats died, they sank to the anoxic bottom, sequestering massive amounts of carbon. Over the course of roughly 800,000 years, this azolla event pulled so much CO2 out of the atmosphere that it is credited with transitioning the Earth from the greenhouse Earth of the Eocene to the icehouse Earth we live in today. Once again, a single plant type triggered a global climatic shift, the future of plant-Earth interactions. As we look to the future, the role of plants remains central. We are currently in a period of global greening. Satellite data shows that the Earth is getting greener as rising CO2 levels fertilize plant growth. While this might seem beneficial, it brings its own disruptions. Altered water cycles, changing fire regimes, and shifting ecological zones are all consequences of this new botanical adjustments. However, the most significant plant interaction of the Anthropocene is agriculture. We have replaced complex, deep-rooted native forests with shallow-rooted monocultures of wheat, corn, and soy. This reverses the Devonian dynamic in some ways. We are increasing erosion but decreasing the deep chemical weathering that sequesters carbon. We are also synthetically replicating the nutrient runoff crisis with our fertilizers. The dead zone in the Gulf of Mexico is a yearly reminder that the connection between land management and ocean health is direct and immediate. Conclusion. The story of how plants triggered mass extinctions is a humbling corrective to the anthropocentric view of history. We often view ourselves as the first species, capable of altering the planet on a geological scale. But we are following in the footsteps of the humble moss, the pioneering liverwort, and the mighty Archaeopteris. They were the original terraformers. They did not need factories or internal combustion engines to change the climate. They only needed enzymes, roots, and time. The late Devonian mass extinction stands as a monument to the power of biological innovation. It demonstrates that life is not a passenger on Spaceship Earth. It is the crew, and sometimes the hijacker. The forests that we cherish as symbols of peace and stability were born in violence. Their roots are stained with the chemical legacy of a suffocated ocean. To walk through a forest is to walk through the machinery that once froze the world. The silence of the extinction is gone, replaced by the rustle of leaves, but the mechanism remains. The plants are still working, still weathering, still breathing. The balance is maintained only by the consumers that eat them and the decomposers that rot them. It is a delicate truce, forged in the catastrophe of the Devonian, a reminder that in the history of our planet, green is not always the color of life. Sometimes it is the color of doom. The specifics of the biotic crisis. To delve deeper into the scientific true aspect, we must examine the specific losses. The biological severity of the Devonian extinction is estimated at the loss of 70 to 80% of all animal species. In the marine realm, the losses were catastrophic for the brachiopods, a group of shelled animals that were the dominant filter feeders of the Paleozoic. The spiriferid and atripid brachiopods were decimated. The trilobites, which had survived the Cambrian and Ordovician periods with great success, lost the majority of their diversity, never fully recovering their former glory before their final extinction in the Permian. The tabulate corals and stromatoporoids, the builders of the great Devonian reefs, were virtually wiped out. This led to a reef gap in the geological record. For millions of years, there were no large coral reefs on Earth, only microbial mats. This collapse of the reef ecosystem had cascading effects on the biodiversity of the oceans, as reefs serve as the nurseries and feeding grounds for a vast array of species. The conodonts, eel-like vertebrates whose tooth-like microfossils are used to date rocks, suffered severe losses but managed to survive. Their rapid evolution and extinction pulses provide the high-resolution timeline that allows geologists to correlate the extinction events with the geochemical signals of anoxia. On the vertebrate front, the loss of the placoderms is the most dramatic. These fish represented the pinnacle of vertebrate evolution at the time. They had evolved live birth, complex jaws, and armored protection. Yet their reliance on specific shallow water environments made them vulnerable. Their extinction paved the way for the modern dominance of actinopterygians, ray-finned fishes, and chondrichthyans, sharks and rays. In a very real sense, the dominance of the fish we eat today is a direct result of the Devonian plants killing off their competitors, the soil, as a reactor. The soil that developed during the Devonian was not just dirt, it was a biogeochemical reactor. The evolution of root hairs increased the surface area for nutrient absorption and acid secretion. Plants also began to produce organic litters, leaves, twigs, and bark that accumulated on the soil surface. As rainwater percolated through this litter, it picked up dissolved organic carbon, forming humic and fulvic acids. These organic acids are powerful weathering agents, capable of breaking down minerals that are resistant to inorganic acids. Furthermore, the stabilization of soil by roots increased the residence time of water in the regolith. Instead of running off quickly, water stayed in contact with the rock for longer periods, allowing for more complete chemical reactions. This intensification of the hydrological cycle at the soil-rock interface was the engine of the global cooling. The black box of the Devonian. Scientists study the Devonian extinction by analyzing proxies, indirect evidence preserved in the rock record. Carbon isotopes are the most important. Carbon comes in two stable isotopes, C12 and C13. Life prefers the lighter C12. When massive amounts of organic matter, plants and algae are buried and removed from the system as black shale or coal, the remaining pool of carbon in the ocean and atmosphere becomes enriched in the heavier C13. The rock record of the late Devonian shows distinct positive excursions in C13. These spikes tell us that massive amounts of organic carbon were being buried. This confirms the hypothesis of widespread anoxia, which preserves organic matter, and the rapid drawdown of CO2. Strontium isotopes derived from the weathering of continental rocks also show a shift that indicates a massive increase in erosion and weathering of continental crust during this time. The chemical fingerprints are undeniable. The land was being eaten away, and the oceans were paying the price. The role of mycorrhizae. A critical, often overlooked partner in this planetary heist was the fungi. Plants did not conquer the land alone, they brought allies. Mycorrhizal fungi form symbiotic relationships with plant roots. The fungi provide the plant with phosphorus and other nutrients they extract from the soil, and in return, the plant provides the fungi with sugars produced through photosynthesis. This symbiosis dates back to the earliest land plants. It is hypothesized that the evolution of this partnership was the key breakthrough that allowed plants to colonize the nutrient-poor rocks of the early continents. The fungi are the true miners. Their microscopic hyphae can penetrate pores in minerals that roots cannot reach. They secrete enzymes and acids that dissolve rock. Therefore, the mass extinction was not just caused by plants, but by the plant-fungi alliance. It was a cooperative effort to terraform the Earth, with devastating consequences for the marine biosphere. The late Devonian extinction serves as a case study in complexity theory. A small change in one part of the system, the evolution of a root, amplifies through feedback loops to create a state shift in the entire system. It illustrates the non-linear nature of Earth's history. Progress is not a straight line. The greening of the continents was a progressive step for terrestrial life, but a regressive catastrophe for marine life. The recovery from the Devonian extinction was slow. It took the entirety of the following Carboniferous period for biodiversity to reach previous levels. The structure of marine ecosystems was permanently altered. The era of the static, heavily armored reef dwellers was over. The era of the mobile, swimming, active predators had begun. The plants had forced the animals to become faster, smarter, and more adaptable. In the end, the plants won. They successfully colonized the land, transformed the atmosphere, and reshaped the geosphere. They created the soil that feeds us and the oxygen we breathe. But the price of their victory was a mass grave in the Devonian bedrock, a layer of black shale that serves as a silent testament to the time when the trees killed the world. The lesson for humanity is clear. When you change the chemistry of the planet changes you. The biosphere is not a passive victim. It is a powerful, sometimes violent force. We are currently pulling the levers of this machine, just as the Devonian forests did. We can only hope that our reign does not end in the same suffocating silence. The final consideration is the resilience of life. Despite the devastation, life did not end. It bottlenecked, shifted, and exploded into new forms. The tetrapods, forced to adapt to a changing world, eventually conquered the land, leading to the dinosaurs and eventually to us. In a twist of irony, we, the descendants of the survivors, are now burning the fossilized remains of the forests that caused the crisis, releasing that ancient carbon back into the atmosphere. We are reversing the Devonian cooling, unlocking the cage where the plants trapped the carbon 370 million years ago. We are completing the cycle, undoing the work of the first trees. Whether this will lead to a new mass extinction is the question of our age. But the history of the Devonian tells us that the Earth has a long memory, and the chemical bill always comes due. The intricacies of the Devonian flora reveal a rapid diversification. From the Middle Devonian to the Late Devonian, we see the transition from the rhyny-chert flora, small simple plants, to the Archaeopteris forests. This was not a gradual creep, but a biological explosion. The biomass on land likely increased by orders of magnitude in a geologically short window. This suddenness is what made the impact so severe. The geochemical cycles did not have time to adjust. If we look at the stomatal density of fossil leaves from this period, we can actually reconstruct the CO2 curve. We see a crash in CO2 levels that correlates with the spread of forests. We also see evidence of charcoal, indicating that as oxygen levels rose, fire became a new ecological factor. The world was becoming recognizable: forests, fires, ice caps. The alien world of the Silurian was gone, replaced by a prototype of the modern Earth. The ultimate legacy of the Devonian plants is the world we inhabit. They built the stage. They created the atmosphere. They formed the soil. They are the architects of the modern biosphere. But like all great architects, they had to destroy what was there before to build something new. The mass extinction was the demolition phase of this construction project. It was a tragedy for the trilobites, but a triumph for the trees. As we gaze at the verdant hills and the deep forests of today, we should see them not just as scenery, but as the victors of an ancient war, standing atop the ruins of a vanished ocean, their roots deep in the bones of the past. The geological record is a book with many missing pages, but the chapter on the Devonian is written in bold, black ink. It is a story of power. The power of photosynthesis. The power of roots. The power of life to shape the planet. It is a story that forces us to respect the seemingly passive green world around us. They are not just decorations. They are the most powerful geological force the Earth has ever known. And they have killed before.